Hi, so here's some hints on assignment number 8 for Applied Science 246. And again, I encourage you to do the assignments first if you experience any difficulties, and you can come back for this video tutorial on some of the hints. Okay, now the hints is basically some of the potential difficulties I can see for each one of the questions. So problem number 1 is pretty straightforward and asks you to simplify the addition of two same frequency sinusoidal functions. Okay, the formula is given. Okay, and all you need to do is calculate the E and calculate the phi angle based on the formula. But what you need to be careful is you don't want to just calculate the phi angle based on this tan function here. You need to look at the actual location of point P. So for phi angle, okay, the actual location of this point P described by coordinates A and B to determine the actual phi angle. For example, the part B, okay, so E is fairly simple, 3 squared plus 4 squared, which is 5. So what about the phi angle, right? Phi is tan inverse B over A, which is tan inverse. So the B here is -4, and A here is 3. Okay. And if you simply calculate this one here, I think you will probably make some mistake. So you need to look at the actual location of A and B. Okay, so the actual location here, you draw a diagram. This is just B axis, this is A axis here. Okay, so A is positive 3 and B is -4. Okay, so your actual phi angle is here. So your actual phi angle is going to be a negative angle here. Okay, so negative, you'll get negative 53.13 degree. Okay, so then the end result is actually just 5 cosine omega t minus 5, so it becomes plus 53 of this. Okay, so that's basically for problem number 1. Okay, so let's take a look at problem number 2. Now problem 2 is first of all, we have a similar question in tutorial number 9. Okay, so see tutorial number 9 for APSC 246. A very similar question. Okay, in that question, the initial condition is initial velocity is 0, but in this question my initial velocity is 1/10 reading per second. Okay, so take a look at that tutorial notes, and it's posted on WebCT, and you will be able to find the answer there. The only thing you need to be careful is that this is positive negative thing here. Okay, essentially velocity can go when it goes this way, or when it goes this way, when the ball is a swing. Okay, so there are two directions essentially. Okay? So we're talking about translational velocity. Okay, the problem number 3. This is a long question. Well, but actually the question itself is not that difficult. Okay, there's a lot of descriptions here. You have this mass supreme damper system, which is free by vibration because there's no external forcing function there. With the define of a damping ratio and an undamped natural frequency, the solution what we get is this one here, with alpha defined as this, okay, and omega d defined as this. So A and B we don't know. A and B is determined by initial conditions. So this is what the question's for. Assume you know the initial condition y0 and y prime 0. So assume you know that you have something for the initial displacement and you have something for the initial velocity. Then what is the value of A and B in terms of y initial displacement or initial velocity? So this is basically trying to ask you to prove this general solution. Okay, there's no number involved. Just general solution in terms of the initial condition y of 0 and y prime of 0. Okay, yeah. I think you all you need to do is to calculate from here. So calculate y prime and y double prime. Okay, so substitute these two back into your original one there. Okay, so I'm sorry, so you don't have to substitute there, so you just have to make use of the initial conditions basically. Okay, so for example, y of 0, okay, which is your initial condition. Assume you know this. I don't know what it is, maybe 3 or 4 or 5, right? And what's my solution? Solution is over here, right? So at t equal to 0, so alpha is 0, okay, and a cosine omega d 0 plus b sine omega d 0. Okay, so sine 0 is 0, cosine d0 is 1, so that basically e to the power of 0 is 1, so you get a here, right? So this basically means a value is the initial displacement, so that's pretty handy. And what about the b value? So you take a derivative, right? Y prime, take derivative first. So what is the derivative of this function? Look at this derivative function. You will need to make use of product rule. Okay? So alpha e alpha t, okay, and a cosine omega dt plus b sine omega dt, right? And product rule, then plus e to the power alpha t. And what's inside here is negative a omega d sine omega dt plus b omega d cosine omega dt, right? So that's the this guy here. Okay, so then so this is let's say y prime, right? Now I substitute initial condition. Initial condition is you let t equal to 0, right? The t equal to 0, so this term becomes 1. So alpha a plus cosine omega d omega 0, which is basically a plus 0. That's for this whole thing here. The second one, this is 1, and negative a omega d sine 0 is gone, and b omega d cosine 0, which is 1, right? So that's what you get. Okay, and you have already obtained the a value. Okay, so alpha a value is y of 0. Okay, so multiply by alpha, okay, and plus b omega d. And what's alpha omega d, which is what we defined at the beginning over here. This alpha equal to this, omega d equal to this. Okay, so alpha equal to negative zeta omega n y of 0 plus b omega n square root and 1 minus zeta square. Okay, yeah, so that's this side here, and then you can solve for the b based on this expression. Okay, solve for b, and when you solve the b, you can do some simplifications. Okay, so what you're gonna get is b equals to y prime of 0 plus zeta omega n y of 0 divided by omega n y minus zeta square. Okay. So just rewriting to 2 parts. Okay. And what you're gonna get is y prime of 0. Let's rewrite this one back to omega d. Then this term here, omega n is cancelled. So plus zeta, y minus zeta square. Now y of 0, right? So there you go. So which is basically exactly this term over here. Okay? So that's how you prove the y over t, which is general solution here in terms of symbols. Okay, this is what we call symbolic computation. Okay. The next question is giving specific numbers and specific initial conditions, and they're asking you to plot this whole thing. Okay, I think that's pretty straightforward. You can make use of the maple command I included in the assignments, just to change the necessary part, plug in your function, okay, and then do the plotting. Okay? And if you want to know what they look like, to want to verify, you can go to this website to verify your plot. Okay, let's take a look at problem number 4. Okay, now this is question on the question on solving non-homogeneous second-order differential equation. Okay, and using a method of undetermined coefficients. Okay, don't use anything else but method of undetermined coefficients. As we mentioned in the class, you need to make sure before you go ahead and make sure the modification rule is applied properly. See the first question here, the forcing function, okay, is t squared plus 3 sine t. Then you can take a look at an initial guess. Okay, our initial guess is yp for t squared is at squared plus bt plus c, and for 3 sine t, it's m cosine t plus n sine t. Right, so that's your initial guess, but you got to be make sure that if you need to apply modification rule or not. So what we're using here is basic rule plus sum rule here, right? But so let's take a look at the solution of homogeneous one. Okay, the whole solution actually started giving here. You know, it's giving you this one. So you just have to solve the characteristic equation. Okay, 0. And it's very simple. You can factor this into 2 like this, right? So once lambda equal to -1/2, 1 negative. So there are 2 real roots. Okay, so 2 real roots, and so you have 2 base functions, which is one this, nothing to do with actually your forcing function. So you don't have to apply any modification rule for this guy here. Okay, so that's your yp, and you just have to take yp prime and yp double prime and substitute yp prime, yp double prime back into this non-homogeneous ODE and solve for a, b, c, m, n. Or you want to separate, you want to do it separately, that's fine. Okay. So for the second one there, okay, the forcing function is a cosh 2t, and cosh 2d is equal to this one here. Okay, so there are basically 2 forcing functions. One is et over 2, one and the other is e to the power of negative t over 2. Okay. And what we noticed actually the hint sets that e to the power of negative is one of the solution of homogeneous ODE. And if you look at the characteristic equation here, okay, and apparently this is this, so 1 is 2, and 1 is this. So you have one forcing function with this, and the other forcing function is this. Right, so what you have here is e to the power of negative t. That's the part which duplicates one of the solution, the base solution there. Okay, then your base function. Okay, your base function, the selection your yp, the particular solution, is going to be for e to the power of t. Okay, you can select as k. Let's see, k1. I'll call it a. Let's say a e to the power of et, but for this guy here, okay, and you need to multiply t, okay, and with this one here, and that's your initial guess. Oh, there's a 2t, sorry, there's 2t here. Oh, hang on a second. Oh, sorry, this is a cosh 2t here. Now, cosh 2t with the hint says is a cosh t equal to this. So cosh 2t. Okay. So the cosh 2t, okay, is e to the power of 2t plus e to the power of negative 2t over 2. Okay, so as a matter of fact, what's duplicating the base solution, right? What's duplicating the base solution is this portion right here, right? Is this portion. So what we need to do is we need to select our particular solution A, okay, as at e to the power of 2t plus b e to the power of negative 2t, because this e to the negative 2t, the forcing function, is not duplicating with any of the base solution here. It's this e to the power 2t which is duplicating this one here. Okay, so we need to multiply t, or modification rule applied to this forcing function right here. Okay, sorry about that. That's the number 2. Number 3 is the forcing function sine t cubed. Well, I think I already have it here. Sine t cubed equal to this. Okay, so basically your forcing function has 2 parts. One is sine 3t, one is sine t. Okay, so when you're when you're gonna apply the method of undetermined coefficient, we need to use the sum rule plus the modification rule maybe. So let's take a look at this function y prime plus y equal to this. So that's lambda squared plus lambda equal to 0, which plus 1 equal to 0. Okay, so we have lambda equal to positive negative g. Okay, so y1 is cosine t, and y2 is sine t. Okay, so you look at the forcing function, okay, sine t. Now this forcing part of the forcing function happen to duplicate with y2 here, right? So then your particular function, the choice for the particular function, okay, has to be made using not only the sum rule, basic rule, but also the modification rule, right? So the forcing function for, let's say, sine 3t, okay, is a sine 3t plus b sine 3t, a cosine 3t as b sine 3t. And for sine t, this portion, right, this portion of forcing function is going to be c t cosine t plus dt sine t. Okay, so that's basically what you need to be careful at here. Okay, yeah. So the rest of the work is very procedural. So just calculate prime and double prime, and then group all the similar terms for solving for comparative coefficient, solving for a, b, c, d. Okay, let's take a look at this question here, solving initial value problem. Problem number 5, and initial value problem essentially once you get all the a, b, c, d, and calculate prime, and the substitute t equal to 0, and then calculate a, b, c, d. But over here, it's a very similar thing is when you have lambda squared plus 4 equal to 0. So you have lambda equal to positive negative j2. So y1 is cosine 2t, y2 is sine 2t. Now, your forcing function, one is t squared, one is 3t, so there's nothing to do with sine and cosine, so you don't need to have to apply any modification rule here. Your yp will simply just going to be a t squared plus bt plus c, and plus, let's say, d e to the power t. Okay, so that's it, and then you can go ahead and solve it. Problem 6. Now, this is a question to solve a differential using a method of variation parameters. Okay, so number 1 step, always remember you have to make sure the coefficient here to be 1, because the formula we derive in the class are based on ODE with coefficient 1 for the y double prime term. Okay, and this question actually not much triggered here. All you need to do is basically follow the formulas. Okay, follow formulas. So let me see if any integrations that you might have difficulties there. So this is problem 6. There you go. Let me see. Okay, so this question, there is a integration you might complain for part A here. Okay, so if you do it properly, you'll find that your Wronskian is 1, and your m1 of t, okay, is going to be negative y2 of t f of t over w of t dt, which is negative sine t and tan t dt. Okay, so this term here turned out to be negative sine t squared over cosine t dt. Okay, you might find it a little difficulty in terms of this integration. Okay. Again, here is actually a simple application of trig identity. Okay. So what do? You change the sine t squared, okay, into this. Okay. So now I think you should be okay. Okay, so this has become cosine t and dt. Okay. The first one is 1 over cosine t is second t. Okay. Now this is probably now you can make use of integration tables to find the integral of second t. Okay, the integral of second t. The integral of second t is ln second t plus tan t. Okay, yeah. So if there's anything in exam that happens, I think I'll give you a hint what the integral of a second t is. Okay, but here you can definitely look for integration table. Okay? This is nothing I would trick you in the exam. Okay, let's see for part B. Is there any integrals that can be difficult? Let me just see. There. Okay, so for part B, just see. I think you might be complaining about this one here. Okay, for part B, where you're gonna see your Wronskian is e to the power 2t, and your m1 of t, okay, and turn out to be an integral of this. Okay, now, well, I write here, but you have to give the procedures how this integration is arrived. Okay, and how to integrate this one here, you can use a substitution rule essentially. Okay. The top one becomes t squared minus 1 plus 1, okay, and use a 1/2 here, okay, which is 1/2 ln t squared plus 1. Okay, yeah, you don't have to have a negative positive absolute sign here because t squared plus 1 is already good in the 0. Now m2t, okay, is turn out to be this. Now, what's the integral of this one here? And actually, yeah, you should remember this, or you can look at the table. It's basically arc tan t. Right? Remember, actually, we did a few things. Tan, the derivative of tan t is 1 over 1 plus t squared. Okay, so that's basically for part B, possible integrations difficulty over there. Question number 7. Problem 7 is also using method of federation parameters. And in this part of the question here, I don't require you to solve for y1, y2. y1, y2 is a solution for the homogeneous equation. Now, the reason is because this homogeneous equation here, the coefficients, right, they're not constant, they're t. Okay? So we didn't learn how to solve this in terms of using a non-constant function here. So in this question here, the question gave you the two linear independent solutions, okay, for the homogeneous equation. So y1, y2, okay, their solution of ty double prime for this case here plus y equal to 0, okay, and they are linear independent. Same thing, linear independent. If you want to verify, and you're welcome. And what you need to do, basically use the formula for the method for a variation parameter to solve for the particular solution y, p. So right, solve from yp. Now, number 1 step, okay, remember, normalize this function, okay, divided by t on both sides to make it this format. Okay, yeah, before proceed. The reason is because the formula in the class we derived is for anything here to be 1. Okay, if you want to use the formula derived in the class, you have to normalize it first. Okay, let me see if there is any difficulty regarding the integration. No, I don't think so. The only part for part A, okay, you may need to use a simple integrate parts. Okay, for M2 essentially. So M2 is 1 plus t e to the power of t dt. Okay, you'll end up with this. And when you integrate, to this portion here, apply integrate by part. Okay, so that's probably what you need to be careful here. So for part B, do the same thing, normalize it first before proceed, and the integral, same thing. The integral you for an M1, okay, for an M1, you're gonna have to integrate something like this. Okay, so again, integrate by parts. Okay, and you'll be okay. Problem 8. Now, problem 8 we haven't covered in the class, but you actually can solve it. Well, there's just no numbers there. If I plug in a number here, and I'm sure you'll be able to solve it. This is a typical second-order system, right? The question you're going to solve is when omega here, right, equals to the omega n, which is square root of k over n. So basically, it's application of the modification rule here, and it's solving for a general solution of particular yp. Okay, when this is the case, and actually we call it a resonant phenomena. Okay, if you want to wait until next Monday, and we'll be able to solve this. Okay, we'll be able to solve this. But if you don't want to wait, you can go ahead and actually solve it. And just use everything as we call it the symbolic solution, right? This is basically what we call a symbolic solution here. Everything you get in terms of symbols. There's no numbers. Okay. When the omega equals to omega n, and that's when you need to apply the modification rule here. So anyhow, I think we can wait until next Monday to solve this question there. Okay, thank you. Bye bye.